So with this session, we are coming to an end to the chapter on insolvability of the quintic. At the same time, this is going to be the last session of the entire course on Introduction to Galois theory. So this session is going to be a short session. All I'm going to do in this session is to give you an example of a fifth degree polynomial with coefficients from rational numbers that cannot be solved radically, meaning the splitting field of that polynomial is not an extension of Q by radicals. But before we start this example, I want to go through some results from group theory. I'm not going to give you the proof of this. I'm going to just give you the statement of that result. Sn is a symmetric group. Symmetric group of n elements. And H is a subgroup of Sn. Then, if H has a cycle of n of length n and another cycle of order 2, that means transposition, then H is equal to Sn. So the idea here is that we are going to define a polynomial of degree 5 in Q of x and shows that the Galois group of the splitting field of that polynomial is isomorphic to a subgroup of S5, and that subgroup has a property that it has got a cycle of order 5 and it has got a transposition, meaning that that subgroup itself is the symmetric group of 5 elements. And S5, we know that it is not solvable, and hence the polynomial cannot be resolved radically. That is the plan. So let us define the polynomial. Let f of x be an irreducible polynomial in Q of x of degree 5. So definitely this polynomial has got 5 zeros. so what the condition on the zeros are like this: with two complex zeros and three real zeros. Then the group of f of x. The group of f of x means the Galois group of the splitting field of f of x is isomorphic to S phi, and which is same as saying that the splitting field or the splitting field or the Galois group of the splitting field is isomorphic to S phi, which is same as saying that f cannot be resolved radically. So if you take any polynomial, any reducible polynomial in Q of x with this property, then that cannot be resolved radically. Now, let K be the splitting field of f of x. Then, for each automorphism on the Galois group of K over Q can be considered as a permutation on S phi, because every automorphism on here maps one of the 5 zeros to another, and that is exactly what S5 is doing. Here we have automorphism, on Galois group we have automorphism, and on S5 we have permutation. So G of K over Q can be considered as a subgroup of S phi. Now we are almost here. We need to find out there is an element in this subgroup whose order is 5, has a cycle of length n. Here n is 5. So we need to find out if there is a element in here whose order is 5. When you say order is 5, then the length of that cycle corresponding to the permutation in S5 is 5. See, if alpha is a, 0 of f of x, then the degree of q of alpha over q is equal to 5. and that implies there exists an automorphism in G of K over Q with order phi. Now all we need to do is we need to find out there is a transposition in here, meaning there is an element in G of the Galois group of K over Q with order 2. So it's assumed that 2 of the zeros are complex numbers. So let alpha is equal to a plus ib be one of the complex number. Then its conjugate a minus ib will be another 0 of f of x. So now we are going to identify an automorphism in the Galois group. So identify the automorphism sigma in G of K over Q that is defined as follows. How are we going to define sigma of a plus ib? It should be either a plus ib or a minus ib. A plus ib means it will be an identity map. So this is going to be a minus ib. Then sigma maps all other zeros to itself. And that means if you take a sigma square is equal to I. That means sigma corresponds to a transposition in S5. So we have a cycle of length 5 and we have a transposition also in 5. That means G of K over Q is isomorphic to S5, which is not solvable. So that is the end of the proof. So we have identified a polynomial of degree 5 in Q of x which cannot be resolved radically, or the splitting field of that polynomial is not solvable. One such example of the reducible polynomial which has got two complex zeros and 3 real zeros is 2x to the power of 5 minus 5x to the power of 4 plus 5. I am not going into the details of how to find out the complex and real roots, but the method to prove is we need to show that or verify verify that it is irreducible, we can use Eisenstein's criteria here. Then we need to prove, find out the two complex roots and find out the three real roots. This involves graphical solutions, so I am not going into the details of this. So we have a example here which is an irreducible polynomial over Q having two complex roots and three real roots, and therefore the splitting field of this is not an extension of Q by radicals. So that is the end of my lectures on Introduction to Galois theory. I tried to cover the syllabus of Algebra 2 paper for Calicut and Kannur universities. I hope these lectures will be helpful for you to prepare the test. Thank you for watching my lectures. Thanks.